We'll talk now about two more theoretical concepts related to functions. We've established through the vertical line test a way of determining whether a representation is a function or not. Domain and range give us a way of saying what are the potential allowable inputs of a function, that's the domain, and what kinds of values can I get as outputs. So it gives us a way of characterizing what the inputs and outputs of a function are. So let's look at the mathematical definition first, and then we'll look at many examples of, given numerical formula for functions, how to compute the domain and range. Okay? So here we're looking at the mathematical definition. So for a function f, the domain is the set of allowable inputs. So what can I feed into the function and get something reasonable? Okay, so we'll look at what kinds of things can destroy the domain shortly. That is, I think the philosophical approach that's correct here is at the beginning, the domain should be everything, and then you start taking things out of the domain because, oh, my function wouldn't be defined at these points for various reasons. Now, the range, of course, is kind of different. It's not the set of possible inputs, but the set of possible outputs. So I think that it's harder to determine the range than the domain. Because the domains, you say, well, at the beginning, everything's possible, and then, okay, I look at the function and take some things out. For the range, you really have to get some understanding of what your function is doing. How does it actually convert the inputs to outputs? I think that requires a little bit more finesse. Okay. Right? So what kinds of things can restrict the domain and range? Well, the range you sort of have to compute by hand, but the domain can be restricted based on intrinsic mathematical properties. Okay? So for example, what do I mean by this? Dividing by 0 is, I'll say, illegal mathematically. So why do I bring this up here? Well, it's an illegal mathematical operation. So if my function is asking me to do that, I'm in trouble. Okay? Whatever points would correspond to division by 0 cannot be allowed in the domain, for example. So if I had f of x was equal to 1 over x, 0 cannot be in the domain. Because that would require dividing by 0, which is not allowed. So this is what I mean by an intrinsical mathematical limitation. Okay. You can also, if you're given the plot of a function, you can sort of see where the function is not defined. You can look and say, oh, well, it's not defined for any of these values, therefore they're not in the domain. Similarly for the range. You can look at what y values are achieved, and given those, you can get some inference about the range. Okay, so I would like to go over sort of your canonical functions. Ones you're very likely to see in questions about domain and range, because they kind of cover all the different pathologies that you'll be expected to know for the CLEP. So we'll start with the function f of x equals x squared. Okay, so just to recall the picture for them, so this guy looks like this. Okay, so it has domain, all real numbers, written from minus infinity to infinity. So full domain, but the range is restricted. It's not possible to square a real number and get a negative number. So it's not possible to achieve any negative numbers in this function, which is why the range is not everything. It only goes from 0 to infinity. Okay? It does not include any negative numbers. So this square bracket here, this means include the endpoint. When you have the curvy parenthesis, this means don't include endpoint. A little notation, though it is very standard notation. Okay, so let's look at kind of the inverse to x squared, which will be the square root of x. So here, the domain is also restricted. Okay? I can't take the square root of a negative number. right? So I'm not allowed to input any negative numbers into the square root. Okay, so in this case, the domain is restricted, no negative numbers, and it's also not possible to get a negative number as an output. So the range is also restricted. Very restricted function. So it looks like this. Only positive or numbers and 0 as inputs, and only positive numbers and 0 as outputs. Let's look at logarithm. This is another nice example of having restricted domain, right? So for the logarithm, you can't put in any number that's not positive. Okay, that is invalid. So for this, the picture of a logarithm is like this. Okay, now actually you can get any negative number as an output. So the range is unrestricted. I can get anything for the range, but I cannot put negative numbers or 0 into the formula for the logarithm. Now to understand why that is, we would want to go back to the definition of the exponential function. Right? We define the logarithm as inverting the exponential. We can show that it's not possible to have negative inputs to the logarithm by going to that formula. That's a little bit technical. It's certainly within your abilities if you understand what the logarithm does, but it's not something that's going to be explicitly tested on the CLEP. So I'm not going to do the theoretical derivation. Okay, now for the exponential function, f of x equals a to the x, here the domain can be everything, but my range is only positive numbers. Okay? So I'm not able to get 0 or a negative number as the output. Now, I just want to draw your attention to the fact that the domain for the logarithm is the range of the exponential, and the domain of the exponential is the range of the logarithm. So they switched, right? Now, this is not unique, okay? If I have a function and it's inverse, then their domains the domain of the first is the range of the second, and the range of the first is the domain of the second. So this is a general principle at work. We're going to define something shortly called an inverse function. And this property of switching the domain and range is not special to exponentials and logarithms, but it's true for any function and its inverse. Now the last one we want to look at is something I already alluded to, which is f of x equals 1 over x. So the picture for this one is good to store in memory. It looks like this. Okay, so the domain and the range are both very close to being everything. The only thing that's not allowed in the domain is x equals 0. That number is also not in the range. It's not possible to input any value of x and get 0 as an output. So both the domain and the range are, should be minus infinity to 0 together with 0 to infinity. Another way of saying this is all numbers except 0. That's sort of the sticking point. Okay. I alluded to the fact that you might be able to infer the domain and range just by looking at a plot of the function. Okay, this is like a nice CLEP question because they don't have to give you a formula. They can just show you a bunch of pictures and say, okay, which one has domain blank? And you look at the picture and you say, well, which of them has as input values that specified range or a specified set of values. So just as an example, you might not know how to plot the function f of x equals x over x squared plus 1. You also might not be able to do the analysis to find its domain and range, especially the range. I think that's the trickier one. The domain is probably going to be everything because the only problem I would have is dividing by 0, but x squared plus 1 is always greater than or equal to 1. But if I show you the plot, you can tell me not only is the domain everything, you can tell me what the range looks like. So here, this tells me that the domain is everything because there's no input values that are excluded, and it also gives me a good estimate on the range. The biggest value achieved is 1/2, and the minimum value achieved is -1/2. So we would guess, perhaps, maybe it's more than guess, we would hypothesize that the domain is minus infinity to infinity, and the range is -1/2 to 1/2, and I include those. So I use these square brackets instead of the parenthesis because I include the endpoints, right? This is just a nice way to sort of test if you really understand domain and range. Look at a picture and tell me what the domain and the range are. Let's look at a few example functions just to go through and run some basic examples. Okay, so here's one. I don't have f of x equals square root of x. I have square root of x plus 1. So I need what's under the square root to be non-negative. So I need x to be greater than or equal to minus 1. Right, so minus 1 to infinity. And the range will be 0 to infinity. Okay, so here's a kind of tricky logarithm, right? So I need, for the domain, 3x plus 2 to be greater than 0. That's when I'll have an allowable input for the logarithm. So this tells me that 3x needs to be greater than minus 2, which means x needs to be greater than negative 2/3. Yes? Okay, so that tells me that the domain will be minus 2/3 to infinity. And here I don't include endpoint. And one can check that the range is still everything. This minus sign here basically doesn't have an impact because the range was already all real numbers. So when I put a minus sign there, well, the things that were assigned positive values are now assigned negative values. Things that were assigned negative values were assigned positive. So the assignments are different, but the total range is the same. All right, here's a nice one. So I have an exponential function, right? The domain was minus infinity to infinity for just e to the x. Adding the plus 2 doesn't change anything. If you like, you can use a cute exponential trick. Say this is e squared times e to the x. So the only thing that depends on x, we already understand. We already know what the domain of e to the x is. It's minus infinity to infinity, and the range is open to infinity, right? So don't include 0. Right, here's a quadratic. So what's the domain? Well, the domain for any polynomial is all real numbers. And I'll write that as a proposition. So something that maybe one would try to prove. All polynomials have domain minus infinity to infinity. Now the range is restricted though. And for this it might be nice to try and draw a picture. Okay, so this value here is of course 2. So the only values that I can achieve with this function are those greater than or equal to 2. So even though the domain is everything, the range is restricted. Right? The range is just 2 to infinity inclusive. Right? Include 2. So even though polynomials have domain all real numbers, the range can be restricted. Okay, here's another one. So what's the domain? Well, it's a polynomial, order 1. So all real numbers. How about the range? Well, we can plot this thing and see what's going on. So at 0, it's minus 7. So maybe something like this. Okay, so it looks like it's going to hit everything, that all y values will be achieved. And that is correct. And I'd like to use this as an opportunity to state a general principle. So maybe we would call this a theorem. It's not obvious. And I'll say all polynomials of odd degree have range minus infinity to infinity. Right, and so this is degree 1, which of course is odd. We will do a very thorough discussion of even and odd numbers in Module 7. More than this, we'll give sort of very precise results. But 1 is odd, 3 is odd, 5 is odd, and so on. All of those polynomials will have range all real numbers. So what we can conclude is that the only polynomials that have issues with range are the even ones. Things like quadratics or fourth degree polynomials known as quartics. Right. Oh, here's a nice one where we have absolute value. Right. So is there anything that can't be input to the absolute value? No, it handles positive numbers, negative numbers, and 0. So the domain is everything. Now the interesting thing here is the range. So recall how the absolute value works. I input a number. If it's positive, leave it alone. If it's 0, leave it alone. If it's negative, I kill off the minus sign. So in particular, the absolute value function only outputs positive, or rather non-negative numbers. So how does this impact the range here? Well, this thing here is always less than or equal to 0. Right? The minus sign switches it from positive to negative. So the whole thing must be less than or equal to 1. So the range is not everything. The range is minus infinity to 1, and I include 1. So this is a nice little thing to draw a picture of. So here's a picture. I get all negative numbers in the range, but the only positive numbers I get are the ones greater than 1 and less than, or greater than 0 and less than or equal to 1. Right? So this is maybe a little bit tricky, right? How did I get this plot? Right? What we'll do now is we'll move on to discussing how to plot different types of functions, in particular how to understand what this negative sign here, which I claim is very important, how that manifests itself in plots, right? For me, all I did is I kind of intuited what this plot looked like. I didn't actually plot any values. I used this negative sign trick to make it easier. So in module or submodule 1.4, we will kind of codify some of these things and try to show you all the flexibility that these techniques offer for plotting.